Yeah, good evening, everyone. On behalf of ConstructX and the ConstructTech Forum, I welcome you all to today's talk on LC3 cement. Today is a very special day to us because today is our first tech talk which we are organizing in this forum. Before we start today's session, I'd like to add a few words about the forum and also about the ConstructX. Kannama is not here. On behalf of her, I'd like to say a few words about the ConstructX. ConstructX is basically a training and consulting firm in the field of civil engineering. They are a group of practicing engineers providing trainings and workshops to college students and also to practicing engineers in firms. They take up architectural design, structural design, interior design, estimation and costing works. Basically, they do end-to-end consulting in the field of civil engineering. And I would like to say a few words about the ConstructTech Forum also. This is a technical forum in the field of civil engineering. I am also part of this, and we have engineers from various divisions of civil engineering a part of this forum. We have concrete technologists, structural engineers, geotechnical engineers, transportation engineers, water resource engineers, interior designers, especially architects, professors, research scholars, and young college students. Ultimately, all of us have come together in this forum to know more and grow together, facilitate learning, and to stay updated to the latest advancements in the field of civil engineering. We have started this Tech Talk series. And today we have with us Dr. Yuvraj Dandapani. He's a postdoctoral researcher in the University of Leeds, UK. He's completed his bachelor's in civil engineering from RMK College of Engineering. He's completed his master's and doctorate from IIT Madras. During his research program in IIT, he has worked along with Professor Manu Sandhanam in many of the consulting projects in major firms. For example, L&T, Saint-Gobain, and other big firms as well. He is one of the key persons who has worked in LC3 cement, and I think he is the right person to talk to us about this cement. So with no further delay, let's hear it from Dr. Yuvraj.
Okay, thanks, Sai. So let me get started. I see a lot of my friends from IIT Madras have joined, so this could be a repetition for a lot of them, but I'll try to keep it as interesting as possible in terms of the delivery. Fine. So I think Sai spoke about this forum. So if you are interested, please reach to us in this mail, and we have a lot of very interesting discussion going on in the forum. So from people in PWD and experienced in the field, so you could find it interesting. So let me come to today's talk, which will be on limestone calcined clay cement for concrete construction. So the work I'll be talking about is primarily done during my PhD research at IIT Madras. And currently, as I said, I'm doing my postdoc here. So this is the brief outline of the presentation. I'll give the context and opportunities why we have to look at new cements or adopt cementitious systems. What are the potential cement substitutes that are available? What are blended cements? And we know there is a lot of apprehensions about blended cements and adopting blended cements directly in concrete constructions. And what are some of the myths that we need to give away and start adopting these blended cements? Give some background about LC3, talk about the different components in LC3. Not much of research, just a few insights about what are the properties that we are expecting, and to bring in confidence from people who would potentially adopt the new cements in the field. I'll also share some of the demonstration projects that we have done with LC3 as a part of the research carried out at IIT Madras. So the context is we are currently in 2020. So you can see here, this is its global cement consumption in the which is plotted for next 30 years. And we expect the consumption of cement to grow nearly fourfolds in India, as well as in other developing countries. And we know cements is one of the energy intensive and emission intensive material. So we need to see how we can elevate this environmental impact of meeting the demand as well as associated emission with the material by the use of more sustainable forms of solution. Of course, the sustainable forms of solution comes in several different layers. And one of the most simplest or the direct form of solution is making the cement itself more environmental friendly. The other layers would be improving concrete designs and making concrete more environmental friendly. A later part would be making the structural systems itself more environmental friendly by optimizing the design itself. But during the course of this presentation, I'll talk only at the level of cement, where how we can make the cement more environmental friendly and without compromising on the properties. So by the use of this blended cements route, which are mainly by the use of mineral admixtures, we can cope up with increase in this demand because we bring in a lot of other alternate resources that are available into our material flow cycle. By doing so, we increase the amount of material apart from the natural resources that we'll use for cement production into the material flow cycle. We can reduce environmental impact, utilize a lot of other resources that are available in the forms of byproducts, and people don't call waste anymore. We have to use a byproduct or potentially downstream utilizable resources, and how we can look at improved concrete performance, which is also important towards the sustainable solution. And the reason we need to work on new cement and the material as such is modern cities are all often described as concrete jungles. And you can see the amount of concrete that is used in just one picture here. And if we want more facts, let's look at the numbers. This is the growth in from UN Environmental Report. This is the growth in the population over the last 50 years. And this is the growth in the cement consumption and steel. And compared to steel, which has only doubled, you can see consumption of cement, especially in the last 3 decades, have nearly grown from 1,000 metric ton to around 4,500 metric ton. So we are looking at a resource which is exponentially growing over the last 3 decades, and it is set to grow for the next few decades as well to meet the demands of housing, infrastructure in a lot of developing economies, right? So come before we go into the LC3 itself, let's look at what is the essential qualities of a cement. Essential qualities of cement, as we know, is you have this plain cement particle which is dispersed in water, and when it reacts over time, and it starts filling the spaces with more and more hydration products. And when this happens, it gains strength over a period of time. That's why we need curing. And when we move from plain cement to just clinker to blended cements, we replace some of these cement particles with what is known as SCM, cement substitutes. And when we do so, these react in different rates. So for instance, if you take cement, nearly 50% of cement react by just the initial few days, this halide, and then most of it happens much more slowly over the period of time. There are several different supplementary cementitious material resources like fly ash, metakaolin, and slag, and all of them have varying levels of reactivity, which means fly ash reacts a bit slowly only after 10 days, and slag and metakaolin reacts slightly at a varying rate compared to other SCMs, right? So all of these resources can be utilized, and you can make more complex cements by having a combination of different resources as such, right? So what are these materials which can be put into cement and concrete to make it environmental friendly? So just dealing with touch of chemistry without going into much detail, you have a wide range of materials, but most of it come within this ternary chart of calcium, silica, and alumina, because these are the elements that are available in the largest quantity on the Earth's crust. And to make a resource like cement, which is used in ample amounts, we need to utilize the elements which are available in large quantities. We cannot go for elements which are available in very minor amounts on the earth crust. So there are materials which are purely siliceous, like silica fume, ricer's ash, bagasse ash, other vegetable ashes, fines from glass, and aluminosilicates, which has both alumina and silica. So these can be fly ashes, which are from thermal power plants, and calcined clays, bottom ashes, volcanic ashes, and some resources which are rich in calcium as well. So these are some calcium rich fly ashes, slag, and there are other resources which are basically less reactive, but still potentially utilizable in cementitious materials. It could be limestone, marble powder, quartz, and iron-rich slags, right? So all of these material react to form basic ingredients, which I'll not talk in much detail, which is called CSH, the binding agent in the cements. Right? So there are several factors that we need to understand before even trying to dwell into new cementitious material as such. There are particular characteristics which are intrinsic to the material, like particle sizes. We want cementitious material or any potential cement-based material to have a very narrow range of particle sizes, right? And they should be reactive in the sense, in a medium of water or alkaline solution, they should be able to dissolve and facilitate the formation of hydration products. And thereafter, the rate at which the material reacts also becomes important. The next would be how much of this material we can utilize and what are the other factors that controls the final formulation of the cement that we know. And there are a wide range of other factors, whether any new cement or a blended cements that is developed, how it behaves at different temperature, whether it requires same level of curing as Portland cement, or whether it could have sustained similar level of internal relative humidity, or how it evolves at different relative humidity. So all of these factors becomes more scientifically important, which I'll just introduce for now and not talk much in detail. Right. So in terms of availability, we saw a wide range of resources, but in terms of availability, you can see from this UNEP report, the lot of these resources, vegetable ashes, silica fumes, slag, fly ash, are quite limited. So when cement itself is projected to consume nearly 4,000 metric ton, we need to have higher amount of these resources which can meet the demand to produce blended cements. And two widely available resources in terms of quantity that can potentially meet these demands are calcined clays and limestones. Again, both of these are natural resources, but I'll talk a bit later how we have potential alternate forms of these clays and limestone, which are downstream material in other industries and byproduct which could be used. Right? So in order to appreciate the new kind of binding material as such, let's look at what happens during cement reaction. So a typical hydration of Portland cement, we all know cement exerts heat. So it happens, a major portion of the hydration happens between the first 20 hours itself, and thereafter it's much slower. So this is a heat emission curve. And when we try to zoom in and have a look at this reacting cement as such, a major portion of early age reaction happens with formation of these hydration products, and at later ages you have other hydration products. So this is how, when we zoom in, take a slice of hydrating cement, keep in a microscope, look at few micron sizes. So these are cement particles. These are the interim spaces where you have water in the beginning, and now you can see a lot of fine hydration products. And with time, this becomes much compact. So you can see this is the same cement, but at a later, about 1 month of curing, you can see in micro structure, it's more compact and dense. That's why we see on site, we say that you need to cure concrete and it gains strength over time because it develops a much more refined and finer microstructure over time, right? And when we take this heat and look at several different forms of cement that most of you are already aware about, like for example, plain Portland cement, a fly ash based binder, high volume fly ash binder, or slag and calcined clay. All of these cements have lower heat emissions, which means it because the blended materials tend to react much slowly and contributes to strength and property development much slower compared to the clinker fuses. But you can see this calcined clay limestone, though heat is less, you can see it start overtaking by 40 hours and it continues to rise. But heat as such alone does not determine how the property evolves over time. So when we make a concrete with all of these cements and try to look at, for instance, a simple measurement of strength, you can see Portland cement and the LC3 systems attains nearly similar strength at 7 days, whereas your fly ash systems have uh, around 30% lesser strength. And of course, we all know and have heard for several years that fly ash cements tend to attain strength, cope up with the strength at later ages, right? So this makes it more interesting, because it could have similar levels of strength and property development like your clinker faces, which people have appreciated over several centuries, last 2 centuries, and have adopted, used to the kind of construction practices that deals with Portland cement and its strength development characteristics. So that's what makes LC3 interesting. So let me try to first briefly talk about what LC3 is. So we all are aware about the PPC cement, which is about 70% of Indian market currently, which has the Portland clinker faces, of course, some gypsum and fly ash. So this is your PPC cement. When you get a bag of cement these days, it's more likely in India that you will get a PPC cement as such, which has fly ash in it. So when we talk about LC3, this has the same Portland clinker to a different amount. In addition, it has calcined clay, so it needs specific characteristics of clay and processing of clay. It has limestone in it, and it has gypsum in it. So by having this component, we are able to create a system which is more efficient in terms of space filling and property development. So in terms of composition, there is nothing specific about this particular composition, but this is the widely adopted one that we are trying to project to the larger market as such, especially to the cement manufacturers. So we are looking at Portland clinker in LC3, which is about 50%. You have calcined clay, about 30%. You have limestone, which is about 15%, and finally gypsum, about 5%. So just like your silica fume or metakaolin, which are high performance mineral additive, you can just have a mixture of this calcined clay and limestone, which is called as LC2, or a mineral admixture, which can be sold as a mineral admixture, where you can use it in an RMC and try to produce directly concretes with LC3. So this is what is the composition of LC3 that we are going to talk about in the later part of the presentation, right? So again, just to briefly introduce, this is a large project where globally several academic institutes are involved, funded by SDC. The leading institute is EPFL, which is in Switzerland, and there is a academic institute in Cuba, in India, IIT Madras, Delhi, and Taras, which are involved in the LC3 project as such. So this is the global LC3 project team that worked on the topic for last 10 years or so. So I'll move into this. So what we look at in terms of the LC3 cement is the combination of different reaction, where for Portland cement, we are used to this chemistry where initially you have CSH forming, calcium hydroxide forming, and other minor reaction products. When we go for blended cements, add any blending material into it, calcium hydroxide is consumed, additional pozzolanic CSH is formed. When we have just limestone in it, it brings in slightly additional complexities, where you have this ettringite phase, which are large needle structures, which are formed initially. These tend to remain stable, so this reaction is avoided. Rather, it starts forming other new hydration products based on calcite particles. So when you have combination of this pozzolan along with limestone, you have this benefit of ettringite remaining stable and other carboaluminate phases forming, and the potential benefit of any blending pozzolanic material, which is pozzolanic CSH formation from calcium hydroxide. So this is the final chemistry that we are looking at. Again, I'm not going to go into specifics, but you need to understand this as the AFT AFM phases, which are stable, and formation of pozzolanic CSH from calcium hydroxide. Right? So it has a combination of different reaction in terms of its big background, like the reaction of the clinker phases is accelerated, the ettringite phases, which are large needle voluminous hydration products, remaining stable. So it contributes more efficiently to the space filling process. It forms new hydration products and have benefits of pozzolanic reaction as usual. So all of this lead to a more progressive reduction in the porosity. That's why the property development, as I showed earlier, was much more enhanced by 7 days, right? So these are the two reaction mechanisms, but how LC3 varies from your fly ashes, it's because of the reactivity. So the metakaolin or the calcined clay phases as such reacts much more faster. It's like a rabbit to in terms of forming your basic binding ingredient CSH compared to fly ash, because it forms your have high reactivity and forms your pozzolanic CSH quite rapidly. It contributes to development of properties also quite rapidly as such, right? And so we just looked at what are the different blending materials, how calcined clay contributes to reaction, and how limestone also comes in as additional component. How do we see it holistically as a final product, right? So this is a schematic which is available from this LC3 Technical Resource Center. So if we took look at typical Portland cement clinker, you just have the manufacture of this clinker phases, where you need to heat to about 1450 degrees Celsius. Finally, the produced clinker will be mixed with ground gypsum and brought in as a Portland clinker cement. So when you are looking at LC3, you need clay, which means you have an additional unit which can calcine the clay. What is calcination of clay? I'll talk in detail at later stages. But, right? So this calcination happens at a significantly lower temperature, just at around 800 degrees Celsius. And once this is calcined, you take the calcined clay, mix it with ground limestone. Again, when we say limestone, it's not similar to how limestone is used in clinker production. Rather, it's just a limestone which is brought in, ground to cement sizes and mixed. So when you mix this clay calcined with limestone, you produce what is known as LC2. And when you integrate in this with your Portland clinker phases, you get a bag of LC3. So this is your LC3 cement production as such. So when we look at this, because you are looking at a heating process which is at a significantly lower temperature compared to clinker, and you are mixing other ingredients which does not require any heat treatment, you are able to use less of your clinker, which contributes to emission as well as requires intensive processing. The LC3 cement which is produced as such can have ultimately 30 to 40% reduction in the emissions, right? So let's look at individual components that goes into the production of LC3. So first, clay, which is one of the most important components out of the four. So clay, as we all know, are minerals. This can be classified as 1:1 clays or 2:1 clays, depending on the structure. So for instance, your kyalinite clays are 1:1 clays. Other forms of 2:1 clays are montmorillonite, illite, vermiculite, etc. So a lot of these clays are available as overlays, which means these are not potentially pure resources. It has a lot of impurities like quartz mixed with it. So people often don't tend to use it. So the purer forms of clay are usually taken out for production in ceramic industry, paint industry, etc. But the impure forms of clay are not utilized and kept as overlays, right? So there are several tons of these clay overlays that are available in several states across India as well. So these have been mapped and the information is available in public from IIT Madras, and you can look at it if you are more interested to understand these clays. So the clay as such has a very layered structure, which means these are crystalline phases. When it is crystalline and has an organized structure, it's not very reactive. So you need to take this clay, and there are alternate sources of clay which are available, like mining operation. Even your tunneling operation for metro produces a lot of dredging wastes which has some amount of clay in it. And there are many marine dredging operations which also produces a lot of these waste clay. So there are several industries which also produce clay in their downstream or processing activity. And there are also existing overlays which has impurities and not being utilized by the mainstream ceramic and paint industry. So we can take these clays, but these clays are not reactive as such. So to make them react in cement, you need to do a process called heat treatment, which is calcination. So when you take the clay, heat it to certain temperature, we tend to break this clay structure. And once we do that, it becomes reactive. Now this requires an ideal temperature, and what people have identified is typically at around 600 to 800 degrees Celsius, this organized or clay structure becomes highly amorphous, right, more reactive. And when you just heat it for an higher temperature, there is recrystallization and start becoming less reactive due to formation of crystalline phases like gypsite and other phases, right? So there is an ideal temperature to heat the clay, which is theoretically at around 600, but practically at around 800 degrees Celsius. So when you heat the clay, you decompose this crystal structure of clay and produce an amorphous material, right? There are, as I said, there are several different forms of clays, but kaolinite clay is most widely available and most widely used as well. So these 1:2 clays have equal amount of alumina and silica in the process of their chemical formulations, right? So what is present in a clay? So when you take a chunk of clay and again keep it in a microscope and have a look at it, so this is how it looks. So you have some large particles. Of course, these particles are not going to be reactive, right? So, and there are a lot of these fine particles which are present. So when we try to analyze in detail what are these elements, you can have traces of ions, these large particles which are green as silica, which means these are quartz, not reactive. And a lot of these fine particles have mixture of alumina and silica. So all of them are reactive as such, right? So heat treated clay mainly composes of alumina and silica, which are the major component, which have a tendency to react in your cementitious material, right? So moving ahead, so you, as I said, there are several different forms of clay. You have kaolinite, illite, and montmorillonite, and these have been studied. So for example, these are strength development of kaolinite, illite, and montmorillonite clay. As you can visually see from the strengths, kaolinite clays are more reactive and it contributes to strength development similar to your plain Portland cement. The information is available in this document for reading. So what we can clearly see is amongst the clay, kaolinite clays have a greater tendency to react because of the nature of its structure, right? So is all clays required? Can we what sort of kaolinite clays we should be looking for? So in the LC3 project, we looked at several different kaolinite clays. So these are purity of the clays versus concrete strength at different ages, mortar strength, I should say. So what happens is the black bar you see are the plain Portland cement strength. So at around 40% clay content, you are able to produce strengths which are similar to your plain Portland cements, which means anything more than 40%, you're not actually getting much benefits at later ages, except for some increase in strength up to 7 days. So what it tells us, in order to produce a product which is as equivalent or as a strength development similar to your plain Portland cement or your OPC, which people are used to, it is okay to use clay which has only 40% purity. Which means anything about 40% can be intermixed, or other potential benefit is you can start using these impure clays which are not well utilized in a lot of other industries. So let's come to the limestone part of it. So limestone, as we all know, is a calcium carbonate. It's available only 4% of earth crust. So it's available in several different natural forms like chalk, limestone, marble, which are produced by sedimentation of shells over several millions of years. So there are also other sources like marble dust, dolomite, slaking waste, paper sludge, and marl, which is a mixture of clay with limestone. So all of this are potential limestone sources. And there is also a possibility to produce limestone or calcite based minerals by this widely increasingly adopted process called carbon sequestration. So one of the major ways of capturing carbon capturing and storing is you tend to capture in a calcium or magnesium source in terms of calcium carbonate and magnesium carbonate, which means these minerals could be made available for use as a cement blending material. And as we most of you might already know, limestone is already utilized in cement production. So what is new? So that will be the question that might be occurring your mind. So when we use limestone for cement production, we tend to break down this calcium carbonate and release this CO2. Instead, when we directly start using this calcium carbonate into cement, we don't release that CO2 into the system. Of course, it has other benefits, which I'll talk about. And there are also limestone resources available in the existing cement plant. You can say this is at Ariyalur, where there is a huge amount of limestone overlays, which are potentially less purity limestone, which cannot be used in cement production. So they are unable to use it. So these resources can be utilized to meet the increasing demand of producing cement-based material. So what does limestone does inside cement? Limestone is again highly crystalline. It has very low solubility. It doesn't react much, but because it has calcium-rich surfaces, what people have identified it has a tendency for similar tendency for CSH to form on the surface like your C3S phase. So this is your clinker phase where you can see hydration products. Around your limestone also you have a tendency to form your hydration products, right? Again, this is not the only reason. There is a detailed classification which we have worked out and put out in this review document which can be accessed publicly. So limestone has physical and chemical effects. In terms of physical, we call it dilution because it's less reactive. Because these are fine particle, it could have a shearing action on your other phases, and the fine particles could also reduce capillary space and increase the space filling process. And calcium rich surfaces, as I showed previously, can lead to nucleation of CSH. It also accelerates the reaction of your C3S because it dissolves and supplies limited amount of calcium into your pore solution at early ages. And the carbonate tends to stabilize that ettringite and react to form other carboaluminate phases. And there is also chances of these carbonate phases being observed into your CSH, right? So these are the range of different reactions. So what it does, when we look at, if you remember the initial hydration curve of plain Portland cement, so this is the hydration curve. This is with just fly ash, and where your heat release is slowed down, so it starts at a slower rate. The total heat evolved is slow, so that's why we have setting issues with fly ash. And when we have some amount of limestone into it, you can see the curve is shifted this way, which means the system is reacting much faster and earlier, and the slope is also similar to your plain Portland cements because of the acceleration effect and nucleation. So the cement systems start having a synergistic reaction. So there is a lot of this reaction changes that are happening, which leads to difference in properties. So let's look at what is impact of these changes on the properties. So this is with your strengths, which is a primary measure, ultimately what a civil engineer is interested in. So this is your strengths of OPC. This is strengths with just calcined clay at around 40%. And these are strengths with calcined clay limestone combinations. Now you can see some of the calcined clay limestone combinations have a even higher strength than your OPC, not only at 3 days, at around 6 months also, which means the combination of calcined clay, limestone, and your clinker, even at around 50% replacement of your clinker, is able to produce similar strength at 3 days as well as at 180 days. So it's a one-to-one comparison in terms of how construction activities have to be carried out on site in terms of strength development and loading and construction cycle, etc. So we have a product, unlike fly ash cements, where we are not going to have any differences in strength development, no need for additional curing to be straight, as simple as that. So what happens, what is the background of this is because you have a tendency to have a theoretical higher volume of porosity. Again, these are theories that have been put out as on a civil engineering scale, like the discussion we have in this forum, these are not much important, but what I wanted to emphasize is there is sound background on why this happens and why we get such behavior of strength development in the systems. So just to talk more in terms of engineering scale, for concrete constructions, primary need is whether we will be able to produce a range of different concrete types, like low strength concrete, like M30 grade concrete, or an high strength concrete, which can be used for an infrastructure project, M50 grade concrete. So we can produce all of these concretes with LC3. Again, you can see the strength development. There is no much difference compared to your plain Portland cement. Whereas if you produce a similar ultimate strength with your fly ash concrete, the development of strength over time is going to be slower. Of course, there is no harm in using fly ash concrete. It's also beneficial for the environment, but you need to cure it for longer period to attain similar potential. And when you go for higher grade concrete, you can also see OPC or LC3 as similar strength development, and your fly ash concretes cope ups by 2 weeks and thereafter continues to have similar strengths, right? So comparable strengths with your plain Portland cement, major takeaway when LC3 gets standardized and gets available in the market as such. So when does this reaction happen? In order to identify that, what we did was try to look at strength development at different water binder ratios. So this is for your fly ash cement, and this is for your calcined clay limestone combination. So you can see for fly ash, there is a significant jump in strength between 7 to 28 days. That's why we say when you adopt a blended cement like fly ash concrete, cure it for a longer time. So once you cure it, you get potentially good strength development by 1 month. In terms of clay, I think as I showed in the degree of reaction before, it start reacting very early, right from 3 days. So you can see this major jump in strength across a range of water binder ratio happening between 3 to 7 days. So thereafter, it continues very much slowly. So because you have this significant jump in strength between 3 to 7 days, most of your construction activities can continue with similar curing regime or cycles, depending on the strength requirement on site, right? Coming to the durability performance. So blended cements are already quite well known for their durability. So when we did some tests where we immerse concrete in chloride solutions. So most of you might be aware when chloride goes inside your concrete system, reaches the surface of steel, it will start leading to corrosion of your reinforcement. So resistance of your concrete to ingress of chloride becomes one of the key parameters for infrastructure projects where concrete is adopted in a large scale near the shorelines, right? So these are highly sensitive to corrosion and corrosion-based deteriorations. So when we look at LC3, fly ash or OPC systems, these are profiles of chloride, which means how much chloride is present at each depth after immersion of your concrete sample in a chloride solution. So you can see the depth of chloride penetration is only 5 millimeter in LC3. At the same or equivalent time in your OPC, the chlorides could penetrate as high as 20 millimeters. As most of you might be aware, a typical concrete cover is expected to be about 50 to 70 millimeters. So what benefit we get is it takes longer time for chloride to pass through your LC3 systems because it has a very dense and compact microstructure. And when we go to fly ash, we again get a benefit compared to your OPC, but it's not as impactful as your calcined clay limestone systems. So again, this could be converted into a rate called diffusion coefficient, where you can see the ingress of chloride when you consider as at a rate, it is nearly 10 times lower in some of your LC3 systems compared to your plain Portland cement, which is the black marker here, right? So the another key factor is the role of curing. So we all have been told for several decades, so especially in last 2 decades, you need to cure fly ash concrete. It's to get benefits. So what we did was look at sensitivity of LC3 towards curing, because it has high volume replacement of your blending materials. Blending materials, so we try to look at how sensitive it is to curing. So this is your OPC systems. We all know OPC major reaction happens by 7 days. So whether you cure it for 3, 7 or 28, there is not much difference in concrete property when you test it at 28 days, because major portion of your clinker reaction happens in the initial 3 to 7 days. When you take a fly ash concrete, it becomes sensitive. So if you make a fly ash concrete, just cure it for 3 days, don't cure it up to 28 days, test for property. You can see it's even having a lower durability index compared to your OPC concretes. And as you keep curing it more, 3 to 7 days or 7 to 28 days, it gets better and lower compared to your OPC. In terms of LC3, it's quite interesting to see that whether you cure the cement for 3 days, 7 days, or 28 days, because of the rapid pozzolanic reaction of the clay that I was talking about, you get a similar durability parameter, and that absolute value is significantly lower compared to your OPC or fly ash concrete. So as I've explained before. So two major takeaways: there is significantly lower chloride diffusion coefficient in LC3 systems. It's in the range of silica fume concretes. As we all know, silica fume is an expensive byproduct to be used in cement production. So we can utilize calcined clay and limestone in similar scales of performance requirement where silica fume concretes are specified currently in the industry. And it's also less dependent on your curing. So there is, it's not crucial or essential to cure LC3 systems as much as your fly ash systems, which might even need curing beyond 28 days to gain its full potential, right? So I think I gave a broad background and technical background and performance of the cement in this time. And these are some service life estimate that was made in one of the works, research work at IIT Madras. So if you make an OPC systems, because of the chloride ingress, it could have potential corrosion problem at around 10 to 20 years. LC3 system and fly ash systems are more efficient. So in the case of infrastructure projects where we are looking at 100 years of service life, fly ash and LC3 systems tend to have a similar performance on your material service life scale. We are not talking about structure service life, more on a material selection service life predictions. These have similar tendencies for durability performance, right? Again, all these were done in laboratory scale. How do we think it will be suitable for industry to adopt and start using LC3 in large scales? So IIT Madras did a lot of demonstration projects. So this was one of the payment that was done in 2016. Even after around 5 years of service, the payment is quite well. We made some slabs which are just cured with your sackcloths, wet sackcloths, just like how you see in a lot of construction projects, measured durability parameters. So what we saw was just because we have rapid development of microstructure, it tends to have no difference compared to a well cured specimen or the specimen cured like a field like condition. And we also made a payment at Leh Ladakh. This is one of the army camps with LC3, where it will be monitored for freeze-thaw performance over the year. So we have tried to use this concrete in several large-scale projects, and it is expected to be standardized in the next few years. We have submitted a draft standard to BIS, and as and when it comes out, I presume it will be in a state to be adopted by the construction industry quite well. And there are a lot of other studies which has been done at IIT Madras, and when you Google it, you might find a lot of these studies. And if you are interested, do look at the research works from IIT Madras on a range of different characteristics and elsewhere in world where people have worked on LC3 systems as such. So with this, I'll leave you. This is again a demonstration structure that was built in North India with LC3. And it's quite well and even used by people for more than last 5 years. Yes, so with this I'll close and thank you. Sai?
Yes, forum is open for discussion. Any questions?
Yeah, there are few people we are recording, so no, you can just unmute and directly shoot your questions if there is any.
Hi, Yuvraj. This is Anusha.
Hi, Anusha.
Thanks for the presentation. Very nice presentation.
Yeah.
I had doubt in the initial slides where you spoke about the energy and the reactivity of the different systems with SCMs.
Yeah.
Could you please explain me in detail, because I think I missed something.
Okay. The degree of reaction over time.
And you were also speaking about the energy.
Mm.
Yeah.
Okay. Oh,
yeah.
This is the cumulative energy from your heat release curve. So this is the so we know cement reaction is exothermic, no? So when we measure it in terms of energy, cumulative heat. So this is the heat release in energy form, joules per grams of binder. So this is for your plain Portland cement, because a major portion of cement reacts in the early age, so you get higher heat. And again, the heat release from your clinker phases are much more higher compared to heat release from other reactions. So when you use fly ash 30%, you can see the heat release getting lowered because fly ash doesn't react in the initial few days as such. And when you go for 45% fly ash, heat is even more lower because less clinker and fly ash is again inert in the initial few days. When you go for slag, this is the curve for the slag, where you can see maybe up to 1 day it's nearly similar to your fly ash, but post which it takes up and overshoots your fly ash systems because slag starts reacting by that stage. And when you have calcined clay, you can see the rise in the heat development is nearly similar here, little bit shifted and accelerated, but you can see a major rise in the heat development post 1 day, 24 hours. And what we have also seen in a range of different studies in terms of microstructure development, reaction, everything, calcined clay tend to react between 1 to 3 days. So that's why you see the heat release significantly rising by 2 days. Yeah.
Okay, right. Thanks. I have one more question. We were speaking about the limestone additions.
Yes.
What do you think if we add more limestone in OPC systems alone, how can it affect the concrete system?
That is already available in the US, Canadian, and other European standard. It's called a Portland limestone cements. That's also a development which has happened 10 years ago. Unfortunately, in IS, there has been a delay in standardizing PLC cement. But what happens is, unlike your other cementitious phases or ingredients which could react, for instance, this is slag, metakaolin, and fly ash, limestone has a very small tendency to react. So even if you put 30% of limestone in your systems, not more than 4 to 5 grams of your limestone could potentially react. Again, it has to deal with how it interacts with other components in your cement material. It needs more alumina to react. And the other reason is the solubility of limestone is also very low. So at a very small concentration in your pore solution, it gets saturated and it cannot dissolve more. So that's why you can add excess of limestone, but it will not contribute to formation of hydration product like your fly ash or slag or metakaolin.
So you tell we cannot expect more strength by adding only limestone. So SCMs are required.
Yes, SCMs are required, and that's why there is a shift towards having a combination of this limestone and along with an pozzolan. Limestone is also an SCM. SCM classifies everything that can be used to substitute cement. So limestone is also an SCM, but the reaction or the nature of limestone is such that you cannot get much benefits by using them at a higher replacement level. You need an alumina source to complement it, but limestone has its own benefits. As I talked about, it releases calcium, which is not present in SCM. and it leads to nucleation, acceleration of clinker reaction. So all of this can be utilized well by using a combination of your limestone with the pozzolan.
One last question. We have been working on LC3 since almost like 6-7 years now, and LC3 has not reached a very bigger stage, like someone taking using LC3 in the projects or government projects like that. So what do you think that is required in order to take further ahead?
Yeah, so first,
or what is missing?
Yeah, first thing would be standard for that to be packed as a material and sold in the market. You need to have an IS standard. Yeah, that's what currently in progress. Draft has been submitted to BIS, and once standard is out, industries would start producing it. And when it comes out, unlike fly ash, where people are still hesitant to adopt fly ash in several small scale projects, I think we should embrace this LC3 systems much more quicker rather than waiting for 10 or 20 years. That's where dissemination of this knowledge and having this scientific background discussed in public forum could help and ensure that people adopt this system and appreciate it for what it has in terms of its science.
Okay.
Thank you. So to keep it straight, first thing would be to have your standards. Second would be to have a lot of demonstration works to bring in confidence. Of course, IITM is very actively doing it. We had built a building newly also in Chennai, and we are collaborating very extensively with L&T to make sure they adopt LC3 systems in their construction project. So all of this would bring in more confidence in the larger public to adopt the LC3 systems when it gets standardized over the next few years and become available in the market.
Thanks, Yuvraj.
Yep.
Hey, Yuvraj. Great talk.
Yep. Thanks.
Just a quick question, and it's more of a big picture question, not anything specific to LC3. It's a follow-up to Anusha's question. Given that in India, we are not already using, I think about more than, just to put a number out there, more than 70% of the fly ash produced is not being used in concrete, even though it has the potential to be used in concrete.
Yes.
Would you recommend going and mining clay and limestone and adding it to the concrete to form LC3, or would you prefer having something like fly ash, which is already being produced and which is not being used in concrete? Yeah. Or would you recommend some kind of like a quaternary blend of LC3 and fly ash? I just want your thoughts on this.
Yes. Yeah,
without getting too much into the science behind it.
Yes. Quaternary would make it a lot more messy. I think we need to minimize in terms of science how complex it is. But to keep a flat, practical answer, what happens is fly ash resources are present in isolation. So you get fly ash only near thermal power plant. And when you need to transport fly ash for a very long distance, of course, that is going to lead to your emission, which is involved with transportation. So when we look at the broader picture of energy efficient cement being tagged with emission scales, how much emission is per bag of, so there we need to look at the solutions which can be attained at multiple scales. LC3 may not be the only solution, but we need to develop a range of different products, make sure range of different solutions are available for industry. So wherever it's feasible, and once we start taking this emissions factors more seriously into industry processes, for instance, UK has released a document called Net Zero Target by 2050. So across different industry, everyone is being pushed to make sure their processes are being made more efficient and environmental friendly. When government in India also start adopting such policies, we need to make sure industry have a range of available solutions. So if you could produce a fly ash cement, which can produce good performance property, provided fly ash is available, it can be sourced, brought in quickly, adopt it. If you don't have fly ash, don't put excess efforts just in transporting fly ash and contribute emissions by that way. Instead, go towards a solution of mining clays nearby, start using it in the cement production. That's it.
Okay, thank you.
Yep.
Hello,
Good evening, Raj. Vasudeva here.
Yeah.
Hello. Yeah, thanks for the presentation. I just have one doubt. What is the kind of limestone that is added in LC3? I vaguely remember there's something being as primary and secondary limestone.
Yes.
I'm sort of needing more clarity on that. What is added in LC3? Yeah.
Yeah. So as I said, limestone has very low solubility, and even if you add in higher amounts, only a portion of it would react. So we can use impure limestone. How currently specifications classify limestone is limestone with 42% CaO content or above 75% purity is called cement grade limestone. Anything which is lower is called non-cement grade limestone. So what we have observed during the course of the LC3 project between IIT Delhi, Madras and elsewhere is not more than 3 to 5 grams of this limestone could react because it's less soluble. So you can go for an impure limestone, which is only as less as 30% or 40% pure. Rest could just be quartz. As long as you grind it to finer sizes like your cement particles, you can utilize it. And as I briefly touched upon, the contribution of limestone to the reaction process or the chemistry of LC3 is rather having combination of different factors that you can quite well use an impure limestone without worrying about this purity to a great deal. Yeah.
Okay, thank you. I just have one more doubt. Can you please go to the last graph showing that service life?
Yeah. Yep.
Yeah, is that I see there's an OPC curve and then there are two curves in LC3, right? What is the difference between the two curves in LC3?
These are two different LC3 cements made for similar strength. So this LC3 system has similar mixture proportion like the fly ash concrete. This LC3 system has similar strength like your fly ash concrete. So what happens is LC3 tends to attain better strength than fly ash concretes, right? I showed that before. So because that is there, we felt we should be comparing apples to apples and not apples to oranges. So we have compared against both a similar strength LC3 and a similar mixed design LC3 in terms of concrete.
Okay, and why is this LC3 curve of 1s having a higher corrosion initiation probability?
So what happens is, this might be a lot of detail. So as I said, because LC3 can attain better strength development than fly ash, to produce similar strength like your fly ash concrete, you can even produce it at a higher water binder ratio. Unfortunately, when you use higher water binder ratio, we all know durability or the transport parameter is a bit compromised. And when that gets compromised, you tend to have an earlier time required for corrosion. So that's why you see this difference.
Okay. Thanks a lot.
Yeah. So is there any other questions?
This is Gomati.
Yeah. Hey, Komati.
Yeah. That was quite a beautiful talk as usual. So I have a query on the commercialization part. Okay, so see, like any government or the private related projects, whatever we deal with, the first question that comes while we try to execute something at site is, what is the cost of, say, per meter cube of concrete?
Yeah.
So could you throw some light on how much as in comparison this LC3 will cost in comparison with OPC, say, per 50 kg bag or something?
Yeah. So in terms of cost, again, it depends on the scale at which it's produced and get adopted. But on a very simpler form, one can naturally think from the process that I have showed earlier. You need to, so cost involves several different aspects, right? One would be processing cost and the material cost. And because you can process clay at a lower temperature, the processing cost here is cut down. Because you can process limestone without any heat treatment, just grinding, again, processing cost is significantly cut down, right? So when we are having two replacements for Portland clinker, where process is made more at a lower temperature or no processing at all, we expect companies to reduce cost. But that would depend upon amount of LC3 that could be produced, the additional so you need two additional units which cement companies has to put up. One is a calcination unit, other one is a grinding unit for limestone. So though these may not add up to significant initial cost, but still there would be some difference. In terms of cost, clinker currently costs about 8 kg per gram. But if you take limestone, a ton of limestone is not more than a few hundred rupees, right? So that's the cost. So we are looking at comparatively much cheaper material that are being used to replace clinker, and cost has to be low, but industry would have to decide on the cost. So how industry operates is, if they find a greater acceptance towards LC3 in the market tomorrow, they will market it as an high performance cement. Cost might be more, and yeah, it's purely commercialization and how industry adopts it, embrace the technology and start presenting it to market tomorrow.
Yuvraj, extending your answer, I will just point out that OPC price is 340 rupees for 50 kg and PPC is just 320. So I don't think cement manufacturers will give any extra benefit of reducing the clinker, but they might sell in just 23-30 rupees range difference.
Yeah.
Okay, so how I see it was, I purchased some LC2 recently from Paragon. So it costed around, for 50 kg, it costed around 2,500 LC2.
Yep.
So when we are looking into these projects or into the commercial part, and we weren't able to argue much with the project side to, I mean, bring our material inside to the on site or whatever. We weren't able to justify for the cost.
Yeah. So, yes, but what happens is currently it's only the LC3 project team that is creating this material and supplying it in small batches. So what we are trying to do is make sure some of the industry and projects where specification allows to use LC3, they could get access to the material, start adopting it. So it's a matter of scale. When more people start producing it, more cement companies jumps in to adopt this technology. The cost is going to be significantly lower. As I said, we are looking at resources that are widely available. So not much difficult to identify this material or transport this material, and processing requires less intensive processing compared to your clinker. So definitely cost has to be low when the scale is up.
Yeah, thank you, Yuvraj.
Yep.
Here.
Yep.
Yeah, I just have one question. When can we expect this cement to the market?
When can we expect this cement to
market?
Yeah, so we have given a draft standard. Again, it was a year and a half ago, and once standard is out, and we already had some production with cement companies, major cement producers like JK Lakshmi, who produce several tons of cement for the research project. And right now there are some demonstration projects which are done in line with L&T and other companies as well. And once these come out, I would say LC3 is already out there, but it's up to project specifications to deal with it and make sure the material is specified and could be adopted. For a large scale commercial activity, commercialization of the cement as such, we have to await for the standard, and we expect the standard to come out in at least in the next few years, couple of years.
Okay, thank you. And also, I want to add that in LNT, specifically for Kudangulam tetrapod, we are using the LC3 cement.
Yeah, I think Prasad sir was there.
Yeah, he was there in the meeting. I think he's not here right now to talk more about this.
Yeah. So L&T is also adopting LC3 in the Kudangulam. I'm not sure I'm the right person to talk about it. It's industry project, but they will adopt it in one of their major projects in a small scale as a tie-up with IIT. Yep.
Hello. Hi, sir. Good evening. Sir, Ashok here.
Yeah.
With picking up of this precast and modular construction, so I just wanted to know the how good is this LC3 in high early age gain because of this de-shuttering time people look about. So how good is it in early strength gain?
Yes. Yeah. So that's where the early age strength is one of the major benefits with the LC3 systems. So I think I pointed out in the presentation about 7-day strengths and all, and also some strength development curves for 2-3 different grades of concrete. In terms of early age strength, we look at significant development of strength. Talking about precast in IIT Madras, we also did a study with steam cured and other cases, just like how industry would use precast concrete, and we found that it has similar strength development after steam curing also. So I think in terms of early age strength, it's a clear winner, and in all the cases of precast and steam cured conditions, LC3 is good to be adopted. And we have a publication coming up from IIT Madras on steam cured LC3. So.
Oh, okay. Okay, sir. Thank you. Thank you so much.
Hi, Yuvraj. Surya here. Generally, in the production of LC3 cement, what type of clay used? Is it 1:1 or 2:1?
Yes. Yes. LC3, as I pointed out, 1:1 clays, especially kyanite clays, and for the LC3 project, in a larger group, we all dealt with several different types of clays. And what we identify is, as long as your clay has 40% purity and it's kyanite clay, it seems to work fine to produce OPC equivalent properties.
Okay. If modelite and ilmenite clays are like more available in the local area, is it preferable to use that?
Yes. Not as an LC3 form. Yes, you can use the other forms of clay, but what happens is, I think I pointed out to the crystal structure of monomodelanite and ilmenite. We have a cation between the aluminosilicate sheets, and because of these cations, these require higher temperature to first break down the structure. Your illite need to be heated at 950 degrees Celsius. Second, even after producing that energy to heat it, it's not as reactive as kyanite clay. Your kyanite clay, because of the basic clay structure and how it responds to heat treatment, it's more reactive compared to the other clay sources. Of course, there is no wrong in adopting other clay sources, but you need to be aware that you will not get similar development of properties like your kyanite based clay systems.
Okay, thank you.
Yuvraj, I have one more question.
Yes.
So this demonstration building that we have at the Taragram workshop, LC3 is used in what way? Is it used in the form of blocks, or it is used for structure? Or?
Yeah, so this building is entirely made up with LC3. So the blocks were the blocks prepared with LC3 cements, right? And you have RC members also, which were RC members prepared with LC3 cements. There were few comparative columns that were prepared with OPC, I suppose. But IIT Madras team even visited this structure a few years ago and did NDT testing to look at the quality and how it is and all. Yeah. So all the material concrete that you see here, of course, I'm not sure. We also make tiles with LC3 as from Tara side, but I'm not sure those are. But definitely the bricks and the RC members were made with LC3.
Okay, so is there any comparative deterioration with OPC that is noted over these years?
Yeah, I think that's not something to be talked about because it was a study done as a part of the project, but we just tested for NDT qualities and see whether it was okay or not. One good thing is people are using the building for all these years, so it's still stable and then.
Yes, true. I visited there last month, so it looked and worked fine.
Okay,
So,
yeah.
fine, thanks.
Sure, thanks. Okay. Yeah, if there are any more questions, please write to me. And also this new initiative that we have taken. So I thank all my colleagues and friends who have joined. And we had to put Naresh ask some question. Yeah, you can ask Naresh.
Yuvraj, this is Naresh.
Yes.
Hope you're doing very well.
Yeah, thanks.
These days.
Yeah.
Okay, so I doesn't have any technical question. Okay, I just wanted to know, we are doing MS pipe for, I am now doing in all the MS pipeline with more than 1300 dia. There we use cement mortar. Okay. So that cement mortar, what happens during frictional losses, this mortar with the cement MS binding, it is getting toned. I mean, it is getting peeled. So what we can do, whether this LC3 can replace with the binding nature with the steel, so that it has more. Can you hear me properly?
Yeah, I can hear you. Go ahead.
So if those kind of directly with this, pipe materials can be used, this kind of materials. So because I don't have any other questions related to your thing, so related to my thing, I'm asking this.
Yeah, I think the problem you mentioned is a lot more specific in terms of how your MS pipe and concrete is being joined and kept together, and that can be worked out as a joint problem. I don't think changing cement would be the most important or the key aspect to control or change how it works. So I think it's better to deal with that as a joint problem between two different material and find out how new alternate materials like polymer or other could make it more convenient to produce a suitable joint. I'm not sure changing cement would be the best solution to that problem.
Right. Okay. And one more question.
Yeah. Okay. So
one more question. For example, now service reservoirs, okay, that is having more than 20 to 25 years of life. Okay. When we are doing rehabilitation, we will be using grouting thing. So when we are doing grouting, so whether this LC3 cement, I mean, can be used for instead of nominal OPC?
Yes, yeah, definitely. There you can utilize LC3, and so if you say such an operation, something like a flow channel, because LC3 will not have any Portlandite in it, which is one of the hydrate phase which comes out as a leachant. So in terms of leaching based problem, we expect the cements to perform much better. So it will be a more ideal solution for your flow channels and grouting and all. I don't see any problem in adopting this. Yeah.
Okay. Thank you, Yuvraj.
Sure. I think we are done.
Thank you very much for sharing your insights, your experience and knowledge on LC3. It was really a very good session, and we got like kind of more details about the cement which is going to come to market a few years after. So thank you very much. I think most of the participants will enjoy.
Yeah. Okay. Nice. I suppose. Yeah. Thanks everyone for joining.
Thank you once again for accepting to be the first speaker of the forum. Thank you.
Yeah. So we'll send you some feedback forms, hopefully, and we'll have more talks coming out from experienced practical field engineers, people in PWD and other field implementation, as well as academia in the upcoming weeks. We are planning like 2 talks per month. Please do join, and I hope you will benefit from this discussion and interaction. Thank you.
Yeah, thank you one and all for joining. Thank you very much.
Yeah.
We'll meet you all in the next session. Thank you.
Let me stop recording.